This is the third segment of the Module 3 lecture. In the previous recording, we talked a bit about the mean and the median. An important thing to remember is a relationship between the mean and the median based on the shape of the histogram. So remember that the mean is where the fulcrum needs to be to balance the frequency distribution, this little triangle over which the frequency distribution balances. And remember that the median is not affected by large or small values. So if you have a symmetric distribution, the mean and the median are approximately equal. And you can see here the location of the mean and then the location of the median, the one that divides the number of data into equal parts. Now, when you have a positively skewed distribution, then you need to move the fulcrum to the right to balance all these observations to the right. And the median stays put in terms of dividing the 50% of the data is below it and 50% is above it. So if you have a positively skewed distribution, the mean is going to be bigger than the median. Now, if you have a negatively or a left skewed distribution, then in this case, these smaller observations are going to force the fulcrum to move to the left. That is, the median is going to be located or pulled towards the left with respect to the median. The median is more or less where 50% of the data is, to the left and to the right of it. So again, what I'm showing on the figures here is what I'm showing on this table here. And this is important to remember, because sometimes when we're looking at data, we compute the mean and we compute the median, and then say, well, which one should I use? Well, if they're approximately equal, the mean is always the best measure. However, if you have a skewed data, then the mean is not going to be the best representation. The median will be. For example, imagine this positively skewed histogram representing the salary of teachers. And the reason I say teachers is because I remember hearing politicians talking about how teachers have pretty good salaries. Well, but they were talking about the average salaries. Well, here you have the salaries of all the administrators over here. And that, of course, pulls the mean towards the right. And it would appear that the average salary for teachers is pretty good. But if you were to use the median, then you will see that the salary is not as good, because only few people earn a lot of money, but the bulk of the people, or teachers rather, earn much less. So in that case, I will not use a mean to describe the distribution of salaries for teachers or engineers or whatever. The median will be the best representation. All right, so keep this in mind. And now we're going to move on to the measures of dispersion or variation. All right, the very first measure is range, and it's a measure of dispersion. It's very simple. It's just the difference between the largest value and the smallest value of the variable x. And this has been in use just because it's easy to calculate. Is not the best measure of variation because it only uses two values. If you have a large number of values, again, it always uses only two values to compute the measure of variation. So not very efficient. Here's a simple example, and this is the one we've been using, of the 8 cars traveling on a highway, and we measure their speeds. So the variable is the speed in miles per hour. The values of the variable are here, the same that we listed up here. And to calculate the range, we find the largest value, and you scan the data, and you see the largest value is 84. Then you look through the data, find the smallest value, and you see that is 74. So the range is the difference between the largest and the smallest value, which in this case is 10. So the range of the speeds is 10 miles per hour. Or you could say that the spread of the data of these 8 measurements of speed goes from 74 to 84, which is 10 miles per hour. So again, very simple, and is used because it's easy to calculate. Now the variance, which is a more common measure of variability that we use in statistics, is equivalent to the average squared deviations of values from the mean. So each x value, it deviates from the mean, and that deviation we square it, and we divide it by the number of square deviations. That's what we say is the average of the squared deviations of the values from the mean. And so this is the expression for the population variance. For the sample variance is the same as for the population, except that we use the sample mean. The differences of each value from the sample mean, we square that, sum them, and we divide that by the number of observations minus 1. And you say, well, why minus 1? Well, imagine that you have 3 data values, and then you compute the mean. And imagine that for somehow we lose 1 value. You have the mean and 2 of the values. I think that you can use a little bit of algebra, and you can find what the missing value is, because you have the mean, which is the summation of the 3 values divided by 3. But you know the mean, you know 2 values, well, then you can calculate the 3rd value. So we said that we have lost 1 degree of freedom in the variation of the values of x, because the moment you fix the mean and you give me 2 values, then you know automatically the missing value. And this concept will come later on, like when we talk about the t-distribution. All right, so variance is a very efficient measure of variation because it uses all the observed values. And one thing to remember, the variance is always positive because you're squaring the differences. So if you have a negative difference, let's say minus 3, and you square it, well, it's minus 3 times minus 3. Well, it's 9 because the minus times minus is a positive quantity. So remember, the variance is always positive. There are some alternative equations to calculate the variance, and I will explain this a little later in an example, but I wanted to point this out to you because you may see them. I don't remember if this book has them, but I've seen them in many other sources. So again, I'll come back to this, but there are some alternative equations to calculate the population variance. All right, the next measure of variability is the standard deviation, and that is just the square root of the variance. So, and that's what I have here. So the population standard deviation is sigma. So that's just the square root of sigma square. Or if you rather write the equation for the variance, and then you need to add the square root symbol. The same for the sample standard deviation is S, which is equal to the square root of S squared, the sample variance. If you want to use the expression of the sample variance, as we often do, then you need to include the square root symbol. Again, this is an efficient measure of variation because it uses all the data values. Another interesting fact about the standard deviation is that it is in the same scale units as the mean of the observed values. So if the values are in, say, kilograms, then the standard deviation is in kilograms as well. So it's a good thing to remember. So when we compare the mean to the standard deviation, so they're on the same scale units. All right, so let's calculate the variance and the standard deviation. Again, here we have the values of the 8 cars traveling on a highway. These are their speeds, so the variable is speed of cars in miles per hour. The sample size is n, and we already calculated the mean in a previous example. So the mean is known. All right, so let's calculate the variance. So we apply the variance equation. So we take each value of the x variable and we subtract the average that we calculated already. So the first value minus the mean is this right here, and we square that quantity. Then here is the second value, the deviation of the second value from the mean, and we square it. And so on until we get to the last value minus the sample mean, and we square that, and we divide that by 8 minus 1 because this is the sample mean. If you do this calculation, the standard deviation, or rather the variance of these speeds, is 13.126 miles per hour. So in other words, the average deviations from the average, or the average square deviation of the values from the mean is 13.126 miles per hour squared. Remember, we are working on the squared units. And the standard deviation of the speeds of cars is just the square root of the variance. And because we take the square root, then this is in the same units as the variable. So the standard deviation is 3.623 miles per hour. All right, so remember I told you about these alternate equations to calculate the variance. Well, this is because if you're going to do it by hand, it is easier to list your values, sum them. Right here, there's the sum of all the values. Then in the next column, you square each value, and then you sum all the squared values. So with these two quantities and the number of values, then you can put them into this equation. So the sum of the squared values is 49,547 minus the sum of the x value is 629, and you square that, and you divide that by 8. Then you divide the whole quantity by 8 minus 1. And if you do those calculations, you obtain the same value that we obtained using the other formula. And if you want the standard deviation, well, you just take the square root of that number. So again, this is if you want to do it by hand. Now, I wanted to point out to you that Excel can calculate all these things. So you are welcome to use Excel for the homework. In the exams, I will do my best. I hope I don't miss that. But I will not ask you to compute any statistics. If there are statistics, I will give you the values and ask you questions about the statistics. I think from my point of view, it's a waste of time asking you to calculate the mean and the variance and the standard deviation when you most likely are going to be using software to calculate that. So in here, in Excel, open Excel, create a little table with the data, the observation numbers and the data, and I just put the labels of those variables so that I know what I have here. And then to calculate the mean in one cell, I write mean. In the next cell, I type equal, then I type average. And when you type that, Excel helps you, gives you the form of the formula. And so once you type average, you put the first parenthesis, then you click on the first cell and drag it down all the way to the last cell. And that's with this B2 cell all the way to the B9 cell, to 9 and B. And then you close the parenthesis and type enter. That will calculate the mean. And then you can use the median of this expression, the median to calculate the median, the variance to calculate the sample variance, or the variance.p to calculate the population, and so forth. So I posted this example in the Module 3 materials, and it's called Calculate Statistics using Excel. So in that case, I calculated all these statistics, and you can see the formulas, you can see how I structure the data. So again, if the assignment asks you to compute statistics, you're welcome to use Excel to compute the statistics. If you rather use your calculator, you're welcome to do that as well. All right, I'm going to stop here. In the next module, we're going to talk about the uses of the standard deviation, which is section 3.4.